Usually, when you talk about writing software, there's this built-in assumption that the tools you install on your machine dictate the absolute reality of your environment.
Right, yeah, like
Oh.
your local hard drive is the single source of truth.
Exactly. You download a specific program, you install version 2.0, and you expect your system to, well, utilize version 2.0.
It's just the foundational logic of how we interact with our computers, really.
Yeah, you demand predictability.
hmm If you query your machine, you expect the output to reflect the exact state you manually configured.
But step into the world of modern dependency management, and that solid ground starts to completely shift underneath your feet.
Oh, absolutely. It gets wild.
Welcome to today's deep dive. We are unpacking that shift today through a brilliant, highly technical post by a developer named Ang.
Yeah, published on May 27, 2026.
Right. It's titled Notes on Go Programming Part 07, Why Your New Go Project Defaults to an Older N-1 Version.
Which is such a specific title, but so intriguing.
It really is. And Ang actually admits right at the top that they were supposed to be writing about something else entirely, but got totally derailed by a rabbit hole involving how the Go programming language manages its internal dependencies.
Typical developer experience, honestly. Getting sidetracked by a weird error.
Totally. And while, dependency management might sound like niche programming trivia, this seemingly tiny detail leads directly into how the tech industry is actively defending against rampage supply chain attacks.
Which is huge, because decoding this specific software mystery, this strange versioning discrepancy in Go 1.26.0, it reveals a really counterintuitive and frankly brilliant philosophy of software architecture hiding just beneath the surface.
Oh, okay, let's unpack this. Ang's post starts like a classic locked room mystery, but, engineered for programmers.
Oh, I love that analogy.
Right. They sit down at their terminal to bootstrap a brand new project. And we need to walk through this setup because it captures that universal, incredibly frustrating experience of a machine doing something entirely unexpected.
We've all been there.
So Ang opens the terminal and creates a temporary directory, typing cd tmp and making a folder called foobar.
And just to clarify for you listening, they are isolating their environment there, right?
Yeah, exactly. They want to ensure no lingering code from other projects can interfere with this test. Then they check their local Go version just to establish a baseline reality.
Always a smart first step.
They type Go version and the terminal spits back Go version Go 1.26.0 Linux AMD 624.
Right, so that output confirms two really crucial details. First, the underlying hardware architecture is Linux running on an AMD 64-bit processor.
Got it.
And second, and definitely most importantly, the established tool available to the user at that exact second is definitively Go version 1.26.0.
So the foundation is perfectly set. Ang takes the logical next step to initialize a new module by typing go mod init github.com username my module.
Standard command.
Right. And the system creates a new go.mod file. For you listening, if you're not familiar, that go.mod file acts as the master control document for the entire project.
It tells the system the name of the project and outlines the foundational rules for running it.
Exactly. But when Ang opens that newly created go.mod file to verify the setup, it does not say Go 1.26.0.
Wait for it.
It clearly and explicitly states Go 1.25.0.
The cognitive dissonance there is just immediate.
It's so jarring. You are running 1.26. You just commanded 1.26 to generate a new foundational document. And the document claims it is engineered for 1.25.
You'd immediately think your machine is broken.
Which is exactly what Ang thinks. They do what any developer would do and immediately interrogate the operating system to see if the machine is misconfigured.
Right, time to hunt for interfering environment variables.
Yes. They type the Go nvgrep 1.26. They check the Go root variable, which is the physical path on the hard drive where the core language and standard libraries live.
And what does it say?
It points strictly to 1.26.
Okay.
Then they check the Go tool dir, the directory holding the heavy machinery.
Like the actual compiler, the linker, the assembler, all that.
Exactly. And it also points perfectly to 1.26. The version environment variable confirms 1.26.0. They even search the entire environment for the string 1.25, and literally nothing comes up.
Wow. So they mathematically eliminated the possibility of a local configuration error?
Completely.
The system is entirely and exclusively 1.26.0, yet the output is intentionally 1.25.0.
It's like, okay, think of it this way. If I go to the dealership and buy a brand new, top-of-the-line 2026 model car,
I'd
right?
have tracking.
I drive it off the lot feeling great. I pull over, open the glove box, and the owner's manual inside is strictly printed for the 2025 model.
Yeah, you'd be furious.
My first instinct is that someone made a massive logistical mistake on the assembly line. I would be on the phone with the dealer demanding the correct manual. Like, why would a brand new installation hand you old instructions? Isn't this just deeply confusing for new developers?
It is, but what's fascinating here is that Ang discovers through their investigation that this isn't a glitch or an oversight at all.
Wait, it's on purpose.
Totally on purpose. It is a calculated, deeply deliberate change introduced specifically in version 1.26.0.
Huh.
The Go team redesigned the initialization process so that new modules will explicitly target what they call the N-1 version by default.
Okay, meaning whatever the current version is minus 1.
Exactly. The compiler looks at 1.26, does the math, and intentionally steps back one major release to 1.25 when setting up the project's foundation.
But why? Like shifting away from the terminal output to the creators of the language? This feels like they are deliberately holding developers back.
It does feel that way at first glance.
The entire tech industry conditions us to want the bleeding edge, right? If I am forced into the N1 version, aren't I missing out on all the shiny new syntax updates, the new functions, and the features of 1.26.0?
Yes.
Why prompt users to download an update if the software's default behavior is to just ignore it?
You are locked out by default, but that restriction is the entire point.
Oh, really?
Yeah, the Go ecosystem is optimizing for global stability over individual developer convenience. The language operates on a strict, community-wide policy. They officially support the two most recent major releases.
Okay.
So if 1.26 is the newest, then 1.26 and 1.25 constitute the fully supported golden standards of the ecosystem.
But forcing the older version on a brand new project still seems, I don't know, counterproductive.
Think about the historical pain of software updates that lack strict guardrails, though.
Like when things just break randomly.
Exactly. When programming languages push updates and allow everyone to immediately default to the bleeding edge, you inevitably get massive ecosystem fragmentation.
Oh, I see.
A developer casually adopts a brand new feature and publishes a popular library. Suddenly, thousands of downstream projects break overnight because the servers running those projects haven't upgraded their environments yet.
Oh, wow. Yeah, because they're literally missing the new code dictionary.
Right. We have seen entire languages spend a decade painfully migrating between major versions because of this exact problem. By enforcing this two-release support window and defaulting to the older of the two, Go structurally mitigates that fragmentation.
Which fundamentally changes how developers need to interact with their own files.
Yeah.
Ang notes that you have to stop viewing the go.mod file as a mirror reflecting your current local machine setup.
It's not a mirror anymore.
Right. Instead, it is a declaration of compatibility.
Exactly. It acts as a contract with the rest of the world. It states, this code is guaranteed to run successfully for anyone currently existing within the officially supported ecosystem, even if they are one step behind.
That's a great way to frame it. But that leaves us with an obvious limitation.
Which is?
If I am building a project and I genuinely need a new function that only exists in 1.26, how do I get around the N1 restriction? I'm not just stuck.
Yeah, no, you're not stuck. You have to manually opt in. Ang details the exact command required to bypass the default.
Okay, what is it?
You open the terminal and type go mod edit negazo 1.26.0. You are basically forcing the master document to update its compatibility declaration.
See, that feels like unnecessary friction to me. If they just defaulted to the newest version, developers could manually downgrade if they wanted to prioritize broader compatibility.
But the friction is a behavioral mechanism.
How do you know?
By making this an opt-in process rather than an opt-out process, the Go team forces developers to be acutely intentional about breaking backward compatibility.
Psychological guardrails.
Exactly. If the system defaults to 1.26, a developer might casually use a new feature without thinking about the consequences for everyone else. By defaulting to 1.25, the burden of responsibility shifts.
So if you run that command to force 1.26, you are actively acknowledging that you are leaving 1.25 users behind.
Yep, you are making a conscious choice.
Okay, I get the philosophy, but that leaves us with a glaring problem regarding performance.
Okay, lay it on me.
Every new software release brings vital under-the-hood improvements, right? We are talking about Faster compile times, better memory management, heavily optimized garbage collection.
Oh, absolutely. The compiler gets much smarter.
So do I have to sacrifice all of those hardware and compiler performance upgrades just to keep my language syntax restricted to 1.25?
This raises such an important question, which Aang actually addresses by introducing the most conceptually dense part of the post.
Yeah.
How do you maintain strict backward compatibility for the code itself while still extracting the absolute maximum performance from the latest compiler technology?
Here's where it gets really interesting. Aang introduces a second concept to solve this called the toolchain directive.
Yes.
They type another command, go mod, edit distoolchain go 1.26.0. And when they check the go.mod file again, it now contains two distinct lines. It says go 1.25.0 on one line, and directly below it, it says toolchain go 1.26.0.
They have entirely decoupled the language syntax version from the compiler execution version.
It's wild. So think of it this way for you listening. Think of the Go 1.25.0 directive as a standard recipe for baking a cake.
Okay, cake recipe.
It lists the exact ingredients, the precise measurements, the step-by-step instructions. Because it is the 1.25 recipe, it is a proven standard formula that anyone anywhere can follow with total success.
Right, it is perfectly backward compatible.
Exactly. Now, the toolchain Go 1.26.0 directive is the state-of-the-art, hyper-advanced 2026 convection oven you are using to actually bake that recipe.
Oh, that's perfect. The recipe remains identical, but the execution environment is upgraded.
Yes. You, the baker with the new oven, get a faster bake. You get perfectly even heat distribution. You get all the performance upgrades of the new hardware.
Right.
But because the recipe itself is untouched, you can hand that exact same recipe to someone who only has a standard 2025 oven, and they can still bake the cake perfectly.
That's a brilliant way to visualize it. You get the better bake locally, but you don't break the instructions for anyone else.
Right, so the Go directive locks in your standard library, but you get the speed of the new engine.
Yeah, ensuring you aren't using syntax that older environments won't understand. And the toolchain directive acts as that engine command, telling the system, when you actually build this project, use the 1.26 engine to do it.
But the paradigm shift really happens when we look at how this impacts other developers interacting with your code.
Oh, yes. This is where the magic happens.
Because if my coworker pulls my code from a repository, and they only have Go 1.25 installed on their laptop, my code is explicitly demanding the toolchain Go 1.26.0 oven to bake it. But they don't have that oven.
And Aang explains that this is where the Go system becomes automagical.
Automagical. I love that word.
It's so fitting. The toolchain directive is not a suggestion, you see. It is a strict requirement.
Okay.
If your coworker's machine sees toolchain Go 1.26.0 but only has 1.25 installed, the system will automatically reach out, download the 1.26 toolchain in the background, and seamlessly switch to it just to build that specific project.
Wait, hold on, wait.
What?
Having a text file dictate that my computer should go fetch a new compiler without a confirmation prompt feels incredibly dangerous.
Oh, I see where you're going with this.
If I am a developer, I want total uncompromising control over what executable files are being downloaded to my hard drive. Automatically fetching binaries in the background, that sounds less like a feature and more like a massive security vulnerability. Doesn't that risk silent, invisible changes to a developer's machine?
Fetching binaries blindly from the internet would absolutely be catastrophic. You are 100% right to be worried about that.
Right.
But the system is not just wildly trusting a random server. Go mitigates this risk using a rigorous cryptographic verification process.
Okay, how does that work?
When it pulls that new 1.26 toolchain, it checks the downloaded binary against a global tamper-proof checksum database known as SumDI.
SumDI, okay.
It calculates a cryptographic hash, essentially a complex digital fingerprint of the file it just downloaded, and ensures it perfectly matches the official signature published by the Go team.
Oh, wow. So it's mathematically verifying the integrity of the file before it ever executes it.
Exactly.
So if a hacker intercepts the download and alters even a single byte of the compiler code, the hash changes, the verification fails, and the system instantly rejects the download.
It replaces blind trust with cryptographically enforced verification.
That's incredibly smart.
And that mechanism, the ability to safely and explicitly demand exact tool chains, is exactly what pivots Aang's post from a neat technical trick into a vital discussion about global software security.
Because Ang concludes the post with a massive swing regarding these security implications.
They do. They really zoom out.
They point out that dependency and toolchain management are fascinating, precisely because many other programming languages treat them as an afterthought.
Yeah, they just assume the local environment is fine until things actively break.
Right. If we connect this to the bigger picture.
If we connect this to the bigger picture, Ang explicitly links this lack of rigorous management to rampage supply chain attacks.
Right, which we mentioned at the start of the deep dive.
Exactly. Think about the mechanics of a supply chain attack. An attacker doesn't want to hack a single application, right? They want to compromise the infrastructure that builds the application.
Like going after the factory itself.
Yes. They target foundational tools, libraries, or even the compilers themselves.
Going back to our baking analogy, it's poisoning the flour at the mill rather than poisoning the cake at the individual bakery.
Oh, that's a terrifying way to put it, but yes.
Every bakery that buys that poisoned flour is instantly compromised without ever making a mistake themselves.
When programming languages leave toolchain requirements ambiguous, they invite this exact disaster.
Because the language doesn't know what it's supposed to be looking for.
Right. If a project simply asks the environment for, quote, a Go compiler, unquote, it will blindly grab whatever executable happens to be lying around on the build server. An attacker only needs to silently substitute a malicious version of the compiler on that machine. The build system uses the poison tool, injects a backdoor into the final application, and literally no one realizes it because the system was never told to verify the tool's exact identity.
Ambiguity allows malicious components to seamlessly blend in.
Exactly.
So what does this all mean?
Well,
It means the explicit dual declaration system in Go is a foundational defense strategy, right?
100%.
The go.mod file states exactly what the recipe is and mathematically enforces exactly which oven must be used. By removing ambiguity, it completely shuts down the loopholes attackers prey upon.
It transforms the go.mod file from a simple list of dependencies into an ironclad security manifest.
That's a great phrase, ironclad security manifest.
Whether you build the code on your personal laptop, a coworker's machine, or a massive automated cloud server, the environment is constructed immutably.
It's the same everywhere.
The toolchain is downloaded, cryptographically verified, and executed identically every single time. There is no room for invisible, malicious tampering, because the local environment is no longer trusted by default.
So what initially looked like a frustrating, almost nonsensical terminal error
Like creating a 1.26 project and getting a 1.25 file.
is actually a masterclass in invisible software architecture. The N-1 default stabilizes the entire developer community by forcing intentionality and preventing ecosystem fragmentation. Decoupling the language rules from the compiler engine allows developers to extract peak performance without abandoning backward compatibility.
It's the best of both worlds.
And by making those requirements mathematically explicit and cryptographically verified, Go turns every single project into a fortress against supply chain attacks.
It's so impressive. And taking the time to understand these under-the-hood mechanics, it moves us past consuming technology blindly.
Steps.
When you understand the profound architectural philosophy behind a simple text file declaring Go 1.25.0, you become a critical thinker about the foundational systems running our digital infrastructure.
It makes you deeply appreciate the hidden guardrails protecting the software we rely on every day.
It really does.
I want to leave you listening with one final, slightly wild thought to mull over.
Oh boy.
We have just explored how a programming language is treating its underlying toolchain not as a permanent, static installation on a hard drive, but as a fluid, auto-downloadable utility that swaps out on the fly based on what a single text file demands.
Right.
If foundational compiler engines are becoming this fluid, how long until our personal operating systems start doing the exact same thing?
Oh, wow.
Imagine your computer seamlessly swapping out an entire system architecture like spinning up a specialized hypervisor or a micro virtual machine in the background, totally invisible to you.
Just for one task.
Just to securely and perfectly run a single application and then instantly dissolving it the second you close the window. The concept of a static, permanent computer environment might be rapidly coming to an end.
That is a wild thought.
Something to think about the next time you open a terminal and assume your local machine is the single source of truth. Thank you for joining us on this deep dive.
Thanks for having me.
Keep questioning the defaults, keep digging into your own curiosities, and we will see you next time.